All right. Hey, welcome back. This is lecture 4 for DS 4400, machine learning. This is a Northeastern course, and I'm Professor Wu. So, after we've done all these math reviews, today is the class. We're going to essentially accumulate everything, put them together, and learn some machine learning. We're going to start off by going over the notation of maximization and minimization. Now, sometimes we might want to solve a function that looks objective that looks like this. And what's happening here is it's saying that we want to find the x that makes the function, the output of this function, as large as possible. That's what this is saying. So this is a maximization problem. Over here, it's the opposite. We want to find the x such that the output of f of x is minimized. Okay? So one, you're trying to maximize this function, and other one, you're trying to find the input that minimizes this function. That's what these notations mean. Now, in calculus, you may have learned that when you have a function, right, obviously this is a high point, and this point is the low point. So this, when you're trying to find a minimization, the value of 2 would be where the function is the lowest. And we learned that to solve this, this is also the point where the derivative is 0, implying that the function at this point is not going up, nor is it going down. It's just kind of staying flat, right? Whereas this point, it's going up. This point is really going up. So is this point. So all these points are going up, but at this particular point, it's not really going up or down. So the derivative is 0. Therefore, to find this point, all we really have to do is to find the point where the derivative is 0. So this function, right, this function is this right here. What we're looking at is this. So if we just take the derivative, which give us this, and we set it to 0, and then we solve for x. So the x that will give us a 0 derivative is 2. And we can see that this is true. At 2, that's where the derivative is 0. So this is the traditional way to solve it with with calculus, where we take the derivative, set it to 0. However, when we run into more complicated functions such as this, then we essentially need to also take the derivative and set it to 0. But in these cases, it's not really obvious how we can set the w to 0. Right? It could be a really complicated function. So today we're going to learn how to find the minimum point for basically any function, right? For any function. Um, so yeah, to do this, okay, we're going to start by looking at a really simple function. This is the function of a parabola, right? It looks like this, and just looking at the plot visually, you can just visually see that the lowest point would be x is equal to 0, right? At this point is where the x is 0. You can also take the derivative, 2x, and you can see that if you plug 0 in here, the derivative is 0. So this particular example is very simple, but we're going to, for the sake of demonstration, we're going to pretend that we can't take the derivative instead of 0. In that case, how can we still identify the lowest point? The x, where is the lowest point? Well, our strategy is to essentially randomly pick an x value. So we don't know which x is going to give us the lowest point, but we're going to pick a random value, and let's say 2. So we can pretend there's a person at 2. And the strategy is that by looking at the derivative, like if you go this way, is the function going to go up? If you go this way, is the function going to go up? By identifying which way the function is going to go down, this person is going to start walking towards, like incrementally walk towards the optimal solution. Okay, so so this is the general idea of the algorithm. The derivative at a given point essentially tells us whether the function is going to go up and then the function is going to go down, right? So if we go back to the derivative lecture, you'll remember that if the derivative is positive, that means as x increases, so as you walk that way, the function is going up, implying that the opposite direction is going to go down. Right? So that's what it's implying. So if the derivative is positive, it's kind of telling you that you want to head towards the left, right? You want x value to be at some negative. So you're at 2, you want to add a negative value, so you kind of go down a bit. And conversely, if the derivative is negative, that means as you increase x, right, your function is going downward. So if you have a negative, then your next value of x is you want to take your value of x now and add some positive value. So if you have x at this point, you want to add some positive value so you start walking towards the optimal solution. So you know which way to go down by looking at the derivative. Essentially, you want to do the opposite. If the derivative is positive, you want a negative, right? You want to add negative to where you are now. And if the derivative is negative, then you want to add a positive value to where you are now, right? It just tells you which way to go. So it's the opposite, right? You do the opposite of the derivative. So this gives us an interesting algorithm. Where we are now, if we calculate the derivative at this point where we are now, and then take the opposite of that. So if we combine this, this will give us the next location when we take a step. And then we can take another step and another step. So let's take a quick example and see that starting at this point 2, right, we have this guy here starting at point 2. Okay, well, what this is the function is x squared, right? And the derivative of this is 2x. So this gives you this. Therefore, at the current location, which x now is 2, see, x now is 2. Therefore, let's just plug this in, right? If we plug x now 2 into the derivative, which is right here, so it will be the derivative is 2x, and you plug 2 in, and that would be minus 4, 2, giving us minus 2. So the person walked from here to here. Well, the person certainly walked towards the correct direction, but the person should have stopped here, right? The person basically walked way too far, like way, way too far. So, so the idea is you don't really want to take a big step. What you want to do is you want to take, you know the direction, but you want to take a small step, and then you do it again and again and again, right? So instead of taking a really big step, we take a smaller step. So what we do is we multiply the derivative by like a small number. It could be smaller than this. You know, this is a number you pick, how small you want the step to be. So if I pick a small step, which is 0.2, instead of arriving to minus 2, which is went too far, we are going to get 1.2, right? So 2 minus 0.8 is 1 minus 2. So we went from 2 to 1 minus 2. So we took a step. So this is good. This time we just took a small step, and we're going to incrementally walk towards this. Now, if we repeat this process, so we're here, we walked here, right? And then once we're at 1.2, we once again plug 1.2 into the derivative, right? And then calculate the next location and then the next location. You will see that we went from 2 to 1.2 to 7.2 to 4.3, 0.43. And little by little, we're going to walk all the way to the solution. This algorithm makes a lot of sense if you understand what a derivative is telling you. Right? By knowing the derivative, it tells you which way to go, left or right. Do you want to go this way? Or you want to go this way? And by knowing which way to go and take a very, very small step, this would allow you to reach the optimal solution. And this is one of the most famous solver. And the question you may get on your interview, which is gradient descent. Like if you're on a job interview, this might be something they ask you. Okay, so this is gradient descent, and the algorithm basically just requires that you take the derivative at the current point, look at which way it's supposed to go, right, and then subtract away your current location or add current location. So we can apply this to higher dimension. So what we had was just one dimension, x, but what if we have two dimension? We're trying to solve for two variables, alpha and beta. Well, for each dimension, you simply pretend it's the dimension itself, right? So if this dimension it's its own thing, this dimension's own thing, you're simply combining them into a vector format so you can calculate them together. So in this particular example, if we take the derivative with respect to alpha, it would be this here. And if we take the derivative with respect to beta, it would be this here. So now we have two functions. So what you can do is you just pick some starting point. You can start walking from anywhere. So depending on where you pick, it might take you longer to get to the final destination. But let's say you pick these 2 points, right? You pick these 2 points, so that's the alpha now. And then after this, you can calculate these values. So you know this number and you can calculate this number. And we're going to pick the step size as 0.2. This implies that you can calculate the next point. So at this point, I want you to take out a piece of paper. This will be one of the in-class exercise and see if you calculate the next location if you just take one single step. Okay? All right, pause the video and we're going to move on. Okay, so the solution of what you should get is, well, if you just plug them in, you should get 6 and 6. And then this is 1.2. We know the starting point from here. Then we just add them up. So after you take one step, this is where you should be. Okay? Make sure you understand like this whole mechanism. Now, I wrote the code that shows you how this works. So over here, this is the function we're trying to minimize. And this is the derivative with respect to alpha and beta. Notice how we can write this thing into a matrix vector format. Over here, we can pull out alpha and beta, which looks like this. So if you have alpha and beta multiplied by this, it would just equal to this. And then you can subtract away the constants here. So I'm going to call this A times W minus C. Okay, so this is just matrix A, vector W, and C. C for constant. So this is just constant value. Therefore, we can calculate the derivative simply by performing a matrix vector multiplication. Okay. So let's see here. I define the A, which is this matrix. I define a C, which is right here. I define a W. So I initialize our starting point. This is where we're going to start walking. So alpha and beta is 2 and 2. I just picked this. And I know ahead of time that the solution is 1 and 1. So you should incrementally walk towards 1 and 1. So after that, I define the function, which is, I just copied it from here. So they're the same function. Once I copy the function, then now we're ready to write gradient descent. Now, remember, we can calculate the derivative by doing AW minus C, which I showed you, AW minus C, right? So which is right here, AW minus C. Okay, after that, I then run the gradient descent. I take the current W position, subtract the step size times the gradient. So this was the gradient, and the gradient goes here. And I put that in a loop. I just do that over and over again, right? And every single time I do that, I calculate the existing value and append it to a list. So what I'm doing is I want to see that as I run gradient descent, what's happening to the function? Is the function getting bigger and bigger and bigger with the new W, or is it getting smaller? Ideally, we want the function to go down, right? Because we're trying to find the W that makes the function as low as possible. So as you increase in gradient descent steps, you should go get lower and lower value. So so the rest is just plotting. So I plotted this out, and you can see that after I run gradient descent, after just 20 loops, I did it 20 times, it basically gives us a solution of 1, 1. I mean, this is 0.9966, so it's pretty close. Right. So this we basically got the right solution after just running it um, um, 20 times. If you want the link to this file to play with it, it's right here. I wrote the code for you. And you can see right here that this is the error, right? This is what you're trying to minimize. So as you increase in gradient descent, every step you're taking, the function is going lower and lower and lower with the new W. Every time you got a new W, it's going lower, right? So basically, it's heading towards zero, right? So this is basically being minimized. You're finding the W value or the alpha beta value that gives you the that gives you the lowest value of the function. So that's what's happening. Okay, so everything else is really just set up. I'm setting it up. So I define the function. The real meat of this is this loop where you're just taking the step over and over again, where you calculate the gradient, and then you just every single time you calculate gradient, you take a step. Then you calculate gradient again, you take a step, and you go back and forth, back and forth. Okay. And that solves the problem. It's actually really easy to solve. If you understand what a derivative is doing, right? You need to know what a derivative is doing to understand what the algorithm is doing. Now, for your next project, I want you to minimize this one here. Okay. Now, remember this is a special notation. Square. When you have a square, it means this here. Okay, that's what that means. And remember, the first step is to take the derivative. So you want to take the derivative of this. And once you have the derivative, then you run gradient descent. And then if you got stuck, right, on how to take the derivative, I showed you how to take the derivative here. Okay. And for the second question, I also want you to take the derivative of this. Right. So you want to minimize this and minimize this. Okay. So I think yeah. So this I also give you the derivative. So if you don't remember how to calculate the derivative of this, I calculate it for you. I hope you do remember because you're going to need it. And let me see. I think you're going to need the x1 value. So let me give you x1 is equal to, I wrote it down somewhere. Yeah, x1 is 0, 1. X2 is equal to 1, 1. And y1 is equal to 0. Y2 is equal to 2. Okay? So your goal is to minimize this. Now, I hope by looking at this example, I mean, the real code is like 5 lines. So it's not that hard. Hopefully, as long as you can find the derivative, you can essentially run gradient descent in a loop. So the key, once again, is to find the derivative and the derivative of this. Then you run gradient descent. Now, if you're really stuck, I did write the code for you, but I you don't you want to be able to do this without my help. So that's the goal. Okay, so that's your next exercise. Hopefully you'll be able to do it. All right, so now we're ready to move on to part 2 after you've done that past exercise. In part 2, we're going to work on this thing called regression. Now, machine learning consists of many different types of learning paradigm. There's supervised, unsupervised, semi-supervised. Basically, there's a lot of them. But among them, supervised learning is the most basic, and it's the first thing that basically all students learn, right? So this is where we're going to start as well. And supervised learning is basically where you collect a bunch of data, and for each data, you will be able to make a prediction, right? And when you can make this prediction, The goal is to find the function. The goal is find the function such that when you plug the data in, the output is as close to the truth as possible. So this particular project was something I actually worked on in my postdoc. And the idea was really simple. What we wanted to do is to collect blood, urine concentrations of pregnant women. Like we will measure like various things in the blood, right? As well as the urine. Once we measure them, we want to predict, then we want to predict when the baby's coming. And so I think you want the baby to come between 37 and 40 weeks. So that's the ideal case. However, however, there are premature cases where the baby comes too early or too late, and that could cause like you know life-threatening danger to the baby and to the mother. So the idea of this prediction model is that maybe you are able to take the input, plug it in, predict when the baby is coming. And when the prediction says it's too early or too late, um, this could be like a trigger warning saying that, hey, there's something in your blood indicating that you might have a premature birth, birth complications. And by doing this, we can have a early warning system to maybe come up with some kind of intervention. So this is a project I worked on before, and this is the example of a regression where you collect data, plug into a function, and make some prediction. The trick here is how do you find this? Okay, how do you find it? And that is regression. So how do we go about doing regression? Well, the goal is of regression is that given some kind of data, and let's say we collect samples, like the blood sample I have here from multiple women. So each set blood sample could be like X1, X2, XN. So we have N samples. And then after we collect the samples, we also collect the labels, which is for this particular case would be when the baby like actually came. So once we have the samples and the labels, our goal is essentially to find a function such that when we plug a sample in, it allows us to predict the label. Right? That's the whole point here. That's what regression does. And the way we can do that mathematically is that we want our prediction and the truth and the actual result. We want their difference, right? This give us the difference between them, which is the error. This is your prediction, this is what happened, and therefore the difference is the error. Now we square them because negative error and positive error, we want them to be treated equally. So this will just make everything positive. So this right here you can view as the error square. What we want to do is if you take all the samples, you find the average error square. That's what this equation is saying. This right here is the average. So this is the error square and this is the average square. It's also called the mean error square. So you know the mean means average, right? Mean error square, right? That's what this means. So what we want to do in regression, once you have this way of measuring your average error, is you want to find a function. You want to find a function such that the mean average square is minimized. Okay, minimize. We want to minimize it. So we are trying to solve this problem here. Now, we today, like earlier today, we just did a minimization problem. And now you understand why we want to do minimization problems. Once we know how to solve minimization problems, then we know how to minimize the difference between the function you have and the actual true output. Okay. Now, having this is not enough because there are like infinite number of functions, right? So it's very very difficult to find the function you're looking for. So to simplify this problem, instead of searching for a function, we basically perform some tricks. Okay, so the key takeaway from this is for you to understand what this objective is doing. This objective is measuring the average error. And what you're doing is you want to find a function that minimizes the average error. That minimizes the average error. Okay? So, how do you go about doing this? Well, well, this is what we're trying to solve. What we can do to minimize this, because finding like a function is very hard, is that we make some assumptions about this function that makes our life easier. And the assumption we can make is that the function is really a combination of other functions. So we're going to call phi 1, phi 2, phi 3, right? So these are functions that we make up. We can just make up a bunch of functions. And we are saying that the true function is some kind of combination of these. So we don't know. We we don't know what the weights are. What we do know is we pick these functions ahead of time. So we know what they are. And then if we can find the weights, the combinations of how they combine together to form this, right? Then we found the function. So we can, what we're saying is we're representing the function this way. And this right here, by making this representation, it allows us to solve this problem like much easier. Okay. So the next question is, okay, well, we don't we now that we assume the function is a bunch of other functions, how do we pick these functions? Okay, how do we pick them? How do we pick them? Well, to pick them, well, educated guesses. Well, we'll start from there. I mean, there are other ways, but we'll start with educated guesses. So let's look at this plot here, right? This These are the data. If you have this point, it goes here. You have this point, it goes here, right? So this right here, by looking at the plot, you can make an educated guess that if you have a line, then it probably does a pretty good job of predicting, right? So in this particular case, if it's a line, then what we could do is we can pick the equation of a line, right? Well, if it's the equation of a line, that implies that we have phi 1, the first basis, and the second basis as this as the equation of the basis. So let's take a look. So like I said, function is a combination of the bases, right? So if the first basis is x, you go here. Second basis is 1, you go here. Then we achieve an equation of a line, right? So by looking at this plot, we can say, well, that's maybe a line, right? So we can now use this basis. And this becomes the equation we're trying to predict, okay? And if we are picking these bases, all right, to find the best function, this approach is called a linear regression. Okay, this is linear regression because, well, it's a line, right? So other times, maybe you'll see a function that looks like this. Well, then maybe what makes sense is for you to have an equation of a parabola, right? Notice how this is the equation of a parabola. Now, just like here, we don't know which line it is, right? We don't know. When we say it's a line, it could be any line. It's not until we find W1, W2 for us to know what the best line is. Over here, it's the same. We don't know W1, W2, W3, right? We just have a structure. And once we have a structure, we can then find the best W1, W2, W3 that like matches the data. In this particular case, then phi 1 is x squared, phi 2 is x, phi 3 is 1, right? So the function, once again, is constructed with a combination of these three, like x2, x squared, x, and 1, right? So what was x1? Well, it's x squared. Then x2 is just x, x3 is 1. So the result here give us the parabola, right? And if we were to use these bases, right, these functions to help us find the best function, f of x, we call this strategy the polynomial regression. Okay, both of them are regression. One is linear, other one is, well, you're using a second order polynomial specifically. But notice something interesting. No matter how you pick the basis functions, no matter how you pick these functions, right, you can always write the function this way. And that's because look at this is a function, and over here is the combination of bases. Well, you can separate out the bases as a vector, and then you can separate out the weights so that once you multiply the weights down, you get this back. Right? Take a second, make sure you see this. Right? Well, it doesn't matter how big this is. It could be 2, 3, 4, 10, and it doesn't matter how big this is. We can always represent this vector as phi of x. Okay? So over here is phi 1, phi 2, phi 3, phi 4, right? But instead of looking at each basis together, we can look at entire vector and just represent that as phi of x. And then we're going to call the weights just w. So f of x can be compactly represented as this way. Okay, so we can rewrite this way. All right, so naming conventions. Now that we learned a whole bunch of concepts, how do we call each component? Okay, so remember, this is our new definition of a function, right? We don't know what a function is, but we're just going to assume that a function looks something like this. Given this new definition, we can split the basis function, the functions that we use, right, to represent the ultimate function here, and we can split them into the weights. So these are color coded. Therefore, the red are all the functions that we use to represent our final function. These functions, the functions we pick to essentially construct f of x, they're called the basis functions. Notice they're all red, right? Color coded. So the red portions are the basis functions. Once again, basis functions are the functions we pick to construct the f of x. And the weights, color coded in blue, they're called the weights. And they essentially tell you the proportion of each function to like combine. So like this could be like 5, this could be 0, meaning this is not part of it. Or this could be 0.5, this could be 0.5, implying it's half and half of each function. So the weights tells you like exactly which function it is. Okay? So these are called basis functions, all right? Each one of them. These are called the weights. And we can rewrite them into a compact vector format, right? So I'm just going to call this vector phi of x, right? Instead of phi 1, phi 2, phi 3, so on and so forth. Phi of x is just going to represent all the phi's. And w is just going to represent all the w's. Okay? Now, this phi of x, that which represents every single basis function, is called a feature map. So this right here is called a feature map. Now, so the feature map is a vector such that you basically put the sample into every basis function. So if you have like m number of basis functions, if you have m of them, then the dimension of this will be m. Okay, so this is going to be m. So let's pay more special attention to the dimensions. So the data is x, right? The data is d dimensions. Therefore, the basis function, just one basis function, is you put the data in, which is d, and the output of the basis function is just one dimension. Okay, so each one of these gives you an output of one dimension. Okay, and then you need to decide how many basis functions you want. If there's like m of them, then your feature map, which has m basis functions, will take d as input, which is d dimension, that's the input dimension, but it will output m dimension. Okay? So you got to get the dimensions straightened out. There's a lot of concept here. So there's a big difference between phi I or phi 1, phi 2, phi 3. These are bases, the feature map is all of them. Okay, and it's much more compact to write it this way. And finally, the weights. So the blues are the weights, the greens are the feature maps, the red are the basis functions. So you want to pause the video, maybe make sure you take a look so you know, got these concepts straightened out in your head. Now, by representing the function with compact vector format like this, then this function can now be written as this. Okay? This is just the compact version. So we're not exactly sure how to solve this. However, we have solved this today, specifically. So we know how to solve this. As long as you know how to get phi of xi, right? Because I think the one we solve looks something like this. So we solve something like this. But this is a vector. So is this. So you just need to convert this vector into this vector, and it's the same problem. So this is why we spend so much time with calculus, linear algebra. It's basically all led up to this equation, just so that you understand what's happening. Again, this right here is a function. This is your function. And you want the output of this function and the true label to be almost the same. So you want the error between them to be almost like as small as possible. And when you take the average, you're trying to find the W such that the average error is minimized. Okay? That's what you're trying to do. Okay? Now, let's say we have the data x1 all the way to xn. And now, remember I told you, this is a vector, this is also a vector. We just need to take each sample, convert it into this vector. So how do we do that? Okay? How do we convert this into this? Well, it's actually quite easy. Let's say these are the data. So this is the data. They're all one dimension, and this is the label. Okay. So if this is the data, then we know that phi, right, is just phi 1, phi 2. Okay. Transpose. They should be transpose here. So this is phi 1, phi 2. So what is phi 1? Well, if we use linear regression, phi 1 is x, phi 2 is 1. So if we plug x1 here, then we're going to get x1 and 1, right? And over here, if I plug x2 here for the second sample, it's going to be x2 and 1. And I plug x3 here, then it's going to be x3 and 1, because these are all 1s, right? And these are all just x. So if you anything you plug here, you get it back. So if you plug x1, you're going to get x1 back. Okay, so what exactly is x1? It's 1. So x1 is 1, so that's here, 1. And then what's x2? We plug in is 2. x3, we plug it in, is here. So this right here, right, is essentially, all the phi's. So phi x1 is this. Phi x2 is this. Phi x3 is this. Okay? Let me write this down. Phi x1 is equal to the vector 1, 1. Remember, we stack them horizontally, but individually they are just column vectors as column. And then phi x2 then is 2, 1. Phi x3 is equal to 3, 1. So now that we have these vectors, life is easy, right? This now implies that we're trying to minimize this objective. And now that we know what this is, we can just plug them in. So there are 3 samples. So right, we're trying to sum up 3 of them. This is if we plug x1, this is if we plug x2, this is if we plug x3 in. And now let's plug it in. We're saying that W1, W2 times x to phi 1, which is this one, will be here. And then W1, W2 times x2, phi x2, then it's here. And again, this will be x3, will be here. So now this right here can be, this is the expansion of 1 over n summation of W transpose phi xi minus yi squared. Okay, so Now you know what this means, and we know how to minimize this, okay, with gradient descent. So the final step is once you do run gradient descent, you find a W such that this whole thing is minimized. So you know W, which is equal to W1, W2. You can now plug that into the function, right? If you know W1, W2, you know the function. Okay? So this is how you identify the function. Okay? This is how you solve a regression problem. First, you set up a problem where your function and the label is it's where you want to minimize. Sorry, you want to minimize the error between your function and the label. And to minimize that, you're trying to find a W that make it as small as possible. And once you find the W, like I said, you know the function. So um, that's if you're trying to do this, your step one is to pick the basis functions you want. Right? You can pick the basis function as x and one. Right? Phi one is equal to x. Phi two is equal to one. All right? You can, and if you do that, it's called linear regression. You can pick another one, polynomial regression. Then these are the basis functions. Of course, you're not constrained with these two. You can pick any function you want. It's just these two are so used so commonly. There's like special name for them, and other people pick other functions. I can even like pick a Professor Wu regression, Prof Wu regression, which I'm gonna define as phi one is equal to log of x, right? And phi two is equal to e to the x. So I can define my own, but most science, basic science, they use these two. Anyways, so pick step one. Step one is to pick the basis functions. Once you pick the basis functions, right, which forms the foundation of your assumption. You then calculate the feature map for each sample. So you put for every single sample, you plug it into the feature map. So if it's linear regression, you plug into this. If it's polynomial, you plug into this. So you will have phi x1, phi x2, phi x3. So now you have the entire thing phi x1, phi x2, so on and so forth. Right? Once you have this, then you find a derivative, right? This is how you calculate the derivative. We did this many times, right? I want you to pay special attention. This is a number, right? The label is a number. This is also a number. So a number and a number is just a number. So this is not a vector. This is a scalar value, okay? Whereas this vector, this is a vector. So essentially, we're looking at a vector multiplied by a scalar value, and we're summing up vectors. So that's what's happening. This is a sum of vectors scaled by this. Okay? So this right here is the derivative. So this means that if you know all these vectors, you know the label, you know this vector, you can do gradient descent, right? The next step is to run gradient descent to keep you pick some starting point W now, and once you do that, you just start walking towards the next one, towards the next one, towards the next one. As you walk more and more towards the next one, your function, right, which is this is your error. Your error is going to go lower and lower and lower and lower and lower, right? As it goes lower, you're picking a better and better W that gives you a lower approximation error. So that's how it works. And finally, you reach a stable point where you get your W is not changing anymore. And when that happens, you would know that you have W1, W2. You simply plug them back into the the the, the function, which was the basis of your assumption, right? So with a linear function, you will have W1, W2. With polynomial, you would have W1, W2, W3. 3 dimensions. So once you find all three of them, right, then you have the function. That's it. So that's how regression works. Okay. So for your exercise today, these are the labels, and this is your, sorry, the y's are the labels, and these are your data points. So 1 1 is right here. 1 1, so that's 1 point. 2 1, 2 2, and 3 2. These are the points, right? And your goal is essentially to find a single line that gives you the least amount of error. So this right here there's no way you can draw a line that can cross all of them. But if you draw this one, it will give you the smallest amount of error. And by doing so, you basically have an equation that gives you the best prediction of all the points. Okay, so I want you to basically run this step, the regression, with a linear one, right? So try to solve this problem, use this data, and run regression. Once you're done, your W1, W2 should equal to 0.5, 0.5. See, if I draw this equation out, that's this. And if you plot it out, it should look something like this. Okay, let's see. Yes. So this one, I wrote the code for you as well. I really would like you to try yourself first. And this one, second exercise, is the polynomial. So your goal is to draw something that like give you the least amount of error. So this one right here, your basis functions are x squared, x, and 1. Okay. So give this a try. If you can finish this, give this a try. And I think that's the end for today.